Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss in this module, which is named Fredholm Equations, General Solutions from the paper Mathematical Physics. So students, let us see what we are going to learn in this module. Now this module will complete the existence theorem for the Fredholm equations. In fact, for the general Fredholm equations, which we started in the previous module. We consider a Fredholm equation of the second kind, f of x is equal to g of x plus lambda, integral from a to b of the kernel k, which is a function of x and x prime, multiplied by the function of x prime and integrated over dx prime, where the kernel k, which is a function of x and x prime, is assumed to be real and continuous function in the range where x lies from a to b and x prime 2 lies in the same range a to b. Now this integral can always be written as a summation in the limit epsilon goes to 0. We can write, for example, the equation as a summation by noting that f of x is equal to g of x plus lambda, integral being replaced by a summation over j from 1 to n multiplied by epsilon and the kernel k, which is a function now of the variable x and xj multiplied by the function at the point xj, where epsilon is equal to xj minus 1, that is, it is the interval, and the lower limit a is equal to x0 or x0 and the upper limit is equal to xn. Now this equation is true for all x, and hence writing it for x is equal to x1, x2, xn, so we can write it for all x's. So we have, for example, the equation for x is equal to xi, f of xi is equal to g of xi plus lambda epsilon summation over j from 1 to n kernel k evaluated at xi and xj and the function evaluated at xj. From the theory of algebraic equations, we have a unique solution provided for a non-vanishing determinant. The determinant in this case we write as dn, a function of lambda, which in the determinant in the first row, the first column, the entry is obviously delta ij is 1, and so 1 minus lambda epsilon k x1 x1, because I first row first column is I is equal to 1, j is equal to 1. First row second column will be I is equal to 1, j is equal to 2, so on and so forth. So the determinant is the determinant n by n, determinant of n by n matrix. Now this determinant can be expanded in powers of lambda epsilon, because epsilon is small, in fact it goes to 0, so we can expand this in powers of lambda epsilon. The 0th order term is simply equal to 1. When lambda epsilon you put equal to 0, so a determinant has only entry 1, 1, 1 along that. The matrix whose determinant is to be determined has only non-zero entry along the diagonal terms, and which is equal to 1 itself. So the 0th order term is 1. The first order term is minus lambda epsilon sum over I is equal to 1 to n k of xi, because when you see, we are keeping only terms now, the first order term. So all the terms which are multiplied lambda square, lambda cube, they all go to 0. So only terms which survive are when 1 is multiplied to the lambda term. So when one can see the first order term is minus lambda epsilon I is equal to 1 to n or sum of k xi. The terms of order lambda epsilon to the power, the whole thing to square, is minus lambda epsilon square by 2 sum over I and j, where I and j go from 1 to n, of within brackets or a product of kxi multiplied by kxj minus the product of k xi xj with k xj xi, which is equal to minus lambda epsilon whole square by 2 sum over I and j of, can write in the form of the determinant of a 2 by 2 matrix whose elements are k xi xj, first row first element, first row second element is k xi xj, second row first column the element is xj xi, second row second column is k of xj xj. So it is understood in the above two equations that the indices ij are not equal in the summation. The factor 2 arises because the double summation, that is k x1 x1 into k x2 x2, is counted twice. It is easy to observe that terms proportional to lambda e to the power s similarly is minus lambda epsilon to the power s by s factorial summed over I, j, k, s from 1 to n of a determinant of a S by S matrix whose elements are, for example, the diagonal elements are k xi xi, k xj xj, k xss, and a ith row jth element will be k xi xj, where I, j, k, s, etc. are a total of s in number, and it is understood in the above equation that the indices I, j, etc. are not equal in the summation. We now can go to the limit n goes to infinity and epsilon goes to 0. The summation in these equations all become integrals of x's. The determinant then in the limit n goes to infinity becomes the determinant of determinant d of function of lambda, where the determinant d a function of lambda is 1 minus lambda times an integral a to b of k x1 x1 dx1 plus lambda square by 2 factorial integral from a to b of dx1, another multiplied by the integral for over dx2 from a to b of a determinant now of 2 by 2 matrix plus a three-dimensional integral, and so on and so forth, with d and lambda and consequently d lambda above are not equal to 0. The formal solution of fx can be written in terms of the cofactors of the matrices. Thus, for a finite n, the solution is formally for xi not equal to xp. So fx of p is equal to gx1 multiplied by the determinant dn of xp xi plus gx2 multiplied by the determinant dn of xp x2 plus so on and so forth till you reach the term gxn multiplied by the determinant of xp xn, the whole thing divided by the determinant dn, a function of lambda, where the determinants dn xi xj are cofactors of the determinant dn of lambda and involve the elements k xi xj. The cofactor for finite n can formally be written in powers of lambda epsilon for I not equal to j. So we can write the determinant dn xi xj in powers of lambda epsilon. The first term is lambda epsilon k xi xj itself. The second term is minus lambda epsilon whole square sum over k from 1 to n of the determinant of a 2 by 2 matrix whose elements are k xi xj, etc. and so on, is equal to lambda k xi xj minus lambda square in integral a to b dxk, a determinant of 2 by 2 matrix plus lambda cube by 3, so it can be expanded in terms of powers of lambda. For xi is equal to xj, determinant a function of xi xj is obviously the determinant d, which is a function of lambda in the limit n goes to infinity. The solution thus formally reads as n goes to infinity that f of x, that is the solution of integral equation, then formally reads f of x is equal to g of x plus 1 upon determinant, which is a function of lambda, multiplied by the integral from a to b of dx prime of, where the integrand is gx prime multiplied by the determinant, which is a function of x and x prime. Thus, determinant d of lambda and the determinant d function of xi, xj are all infinite series. And since they are infinite series, one has to be careful about their convergence. So let us discuss now briefly the convergence of the power series. First, we discuss the boundedness of determinant dn of lambda. Consider the term proportion to lambda 4. The term proportion to lambda n is dn is equal to minus 1 to the power n divided by n factorial lambda to the power n multiplied by n-dimensional integral over dx1, dx2, dxn. The limits of integrals, all integrals are fixed from a to b, and the integrand now is a determinant of a n by n matrix formed out of the kernels k, xi, xj. Let the mod of the kernel k is less than k naught, some number k naught, for x lying between a and b, and y also lying between a and b. Then the nth term is bounded. The evaluation of the bound is a little involved. Now denote k function of xi, xj by kij, and let the n by n determinant on the right hand side be denoted by delta n as Cij. Then from the definition of cofactors, Kij, Cij summed over j is equal to 1 is equal to delta n. Now the n cross n determinant whose elements are Cij we call Cn. Thus from the theory of determinants, Cn is delta n to the power n minus 1. Now delta n is bounded. Since all the kij's are bounded, let us calculate the maximum value of delta n for the given value of fi. So fi is defined as sum of kij square for all values of j from 1 to n, and we keep this to be fixed. Then using the method of Lagrangian multipliers, delta n reaches a maximum as kij vary when the partial derivative of delta n with respect to the element kij minus lambda times the element kij is equal to 0, where lambda by 2 is the Lagrange multiplier. But delta n is sum over j from 1 to n of k1j c1j. Hence, we have c1j is equal to lambda times k1j. So delta n is lambda times sum over j of k1j whole square is lambda times f1. Hence c1j is delta n kij by fi. Proceeding similarly, cij is equal to delta n kij by fi. The elements kij are bounded. Kij mod is less than some number m. Hence fi is also bounded. Fi mod is less than n times m square, can be seen from the above equation. Therefore, delta n to the power n minus 1 is greater than delta n to the power n into delta n divided by nm square to the power n is equal to delta n to the power n plus 1 divided by nm square to the power n. Hence, delta n square is less than or equal to nm square to the power n and is hence bounded. So using thus the bound for delta n in equation 815, we get a bound for the right hand side of the equation 815, which is the nth term in the expansion of the determinant d0 of lambda in powers of lambda. Equation 810 and equation 15. The writing now dn lambda in powers of lambda to the power n as sum over n dn lambda to the n by n factorial, where dn by n factorial is bounded. In fact, the mod of that is bounded. So the mod of dn by n factorial is bounded by nm square to the power n by 2 into b minus a to the power n. So we write a comparison series to test the convergence of the series. We'll make use of the comparison test. So we write a comparison series whose terms are dnn by n factorial comparisons in the nm square n by 2 b minus 1 to the power n. Then in the comparison series, the ratio of n plus 1th term to the nth term. So n plus 1th term to the nth term in the comparison series, we can see to be this is equal to 1 plus 1 by n to the power n by 2 divided by n plus 1 to the power half into m into b minus a. So now in the limit n goes to infinity, 1 plus 1 by n to the power n by 2 is nothing but under root e. Hence, as the limit n goes to infinity, the ratio of the n plus 1th to the nth term in the comparison series goes to 0. The comparison series is thus absolutely convergent. By the comparison theorem in analysis, then the series d lambda is equal to sum over dn lambda from 0 to infinity is equal to dn lambda to the n by n factorial n equal to 0 to infinity is also absolutely convergent for all finite values of lambda, dn being bounded by dn comparison series as given in the equation 8.27 and 8.28. Now we prove the boundedness of the cofactor dn xi xj. Like dn lambda, the cofactor dn xi xj in equation 8.11 also needs to be studied for convergence. Like d lambda, it can be expanded in powers of lambda with the nth term as the nth term of dn xi xj can be written as a power series sum n is equal to 0 to infinity of lambda n by n factorial hn of xi xj. By exactly the same reasoning by which we arrived at the bounds of dn, we get a bound for hn, a function of xi xj, namely hn minus 1 xi xj mod is bounded by n to the power n by 2 m to the capital M to the power n b minus a to the power n minus 1. Thus, just as in the case of dn, we get hn function of xi xj divided by n factorial is less than n to the power n by 2 capital M to the power n b minus a to the power n minus 1 by n factorial, which is equivalent to the term in the comparison series hn comparison by n factorial. We introduce a comparison series instead of the series which we have in the equation. The comparison series is dn comparison xi xj is a series summed over n from 0 to infinity lambda n by n factorial h of n comparison. This is absolutely convergent for all finite lambda. Given the inequality, the series which we have is absolutely convergent by the comparison theorem in analysis. Equation 8.14 is thus the solution of the equation 8.1. We have, of course, been dealing with real functions and kernels. When the kernel is in addition is symmetric, then some more elegant results follow, which we will take up in the next unit, which concerned with such kernels. So students, let us summarize what we have learned in this module. In this module, we consider the Fredholm equation of the second kind, f of x is equal to gx plus lambda integral from a to b over dx prime, or the kernel kxx prime multiplied with the function f(x) prime, where gx is an arbitrary function, fx the unknown function, lambda is a constant, and k as usual is assumed to be a real function and assumed to be continuous in the range of both x and x prime lying between a to b. This equation has been shown to have the solution. So we have proved the existence of the solution of such an integral equation. Thank you.